Alright, welcome back. So we are currently knee-deep into the Hahn-Banach theorem. We have stated and proven the real version of the Hahn-Banach theorem, and now early on in this video I will extend that to the complex Hahn-Banach theorem. So first off, let's have a look again. Let's have a read through. So this one is concerned with complex vector spaces, X, so vector spaces over the complex number field, given a symmetric convex function. So convex functions we used in the real Hahn-Banach theorem. The symmetric constraint here means it's essentially rotation invariant. Then you have a complex subspace Y and linear functional that is dominated in complex modulus by that symmetric convex function on Y. This is everything that's written up to this point. And then the statement is then there exists extension, capital F, linear functional that acts on the whole space, not just the subspace, in such a way that it's still dominated on the whole space in complex modulus by P, and it reproduces that small f when you restrict yourself back to the subspace. Okay, that's the one. So now let's prove it. And as I said, that proof is easier because we did the hard work in the real Hahn-Banach theorem with Zorn's lemma. Now this one, so note that you will have to operate with the real and imaginary part, because those are real for sure. So general fact about complex numbers is this one. When you have a complex number, f of y, and you multiply it by a negative imaginary unit, like here, and you take the real part of that thing, that's precisely the imaginary part. And you can check for yourself. This is an identity that imaginary part of z is just a real part of minus I z. All right. Here z being that f of y, that complex number. All right. So this is true for all y in y, and so by linearity of f for all y in y. Now what I'm going to do is I'm just going to write it as, well, real plus imaginary part, real part f of y plus I, well, imaginary part f of y, but that we already figured out is the real part of minus I f of y, and now I use the linearity because that imaginary unit I can pull inside the f, because f is a linear functional on y, right? And that scalar there out front, the negative imaginary unit, I can just pull inside, right? So we have f of minus iy. That's the linearity. Very good. Now, since by assumption the complex modulus of f is dominated by p of y on y, we have in particular that the real part of f of y is dominated by p of y. And why is this? Well, that's a general inequality. Whenever you have real part of a complex number or the imaginary part, this is always at most equal to the complex modulus, right? Because the complex modulus is sum of squares of real and imaginary part and a square root thereof. So you just drop one term and then you get a lower bound. All right, so you have this. All right, so now if you take this all together, then you realize now you can apply the real Hahn-Banach theorem for, well, the real part of f of y, right? Because that is a linear functional on the subspace y, and it is dominated by p of y, as we just convinced ourselves, okay? In particular that p of y on y. Hence, by the real Hahn-Banach theorem, there is a linear functional f of r, that subscript r for real, so this is real valued, with, well, it is dominated by p Remember, p is real valued. It's a symmetric convex function, but it's real valued, and that you need to make sense of convexity, because convexity deals with inequalities. It's a condition on inequalities. So for all x in x, and fry reproduces your starting object, namely the real part of f of y, when you are back to the subspace. Okay, so this uses the real Hahn-Banach theorem. However, now we use the symmetry, the rotation invariance of p, but by symmetry of p, we have in particular that p of minus x is equal to p of x, right? Remember, the symmetry means that p of lambda x for any lambda on the boundary of the complex unit disk is equal to p of x. So just take lambda equals -1. You get this. So we have this. And now if you use here, since this inequality up here is valid for all x, you're going to use it for x replaced by minus x, right? But then the right hand side, by symmetry of p, is the same as p of x, right? P minus x is equal to p of x. But the left hand side, you have this minus x, but f of r is a linear functional, so you can pull out the minus. So besides that yellow inequality up there, you also have that minus f of rx is at most p of x. Yeah, but these two combined together say that the absolute value of f of rx is at most equal to p of x. Okay, so let's write it down. And thus fr of x is at most p of x on x by linearity, just as I explained it in words, by linearity of f of r, and the fact that f of rx less than or equal p of x holds for all x in x, right? Remember, we are dealing here with vector spaces, so whenever you take a vector in the space and you hit it by a scalar like -1, then that resulting vector is still in the space. You're not falling out. All right, so now we have to set up the actual continuation candidate, and it will be well motivated by this stuff that we did up here. Let's quickly go back. So we used this kind of idea that f is the real part plus I real part, and then f but of minus I the argument. So we will do the same thing here. We define f of x as this continuation that we know to exist by Hahn-Banach, and then fir minus ix. Okay, that's a candidate. Now we have to check that it, well, has the properties that we want. So first, fi of x. What do we have? Okay, let's just replace x by I of x. And then you have fr. So then minus I times ix is just an x. So you have this. But now let's pull out that imaginary unit. So you have fr of x. This comes from this term. Okay. And then the first one, I pull out an imaginary unit. So there is minus I not minus ix, I of x. I of x, right? But remember, the fr is a linear functional. So I can pull in the -1, this guy here, into here, right? So this means this is equal to I fr of x plus I fr minus ix. Okay? Yeah, but what does this show? If you compare this line here with, maybe let's use different color. You compare this line here with this is equal to this. Well, the thing that has happened here is I was able to pull out the imaginary unit from the argument of capital F, right? Yeah, but this means then in turn that capital F is linear, right, on X, on the complex vector space, right? Okay, let's write this down. So F is complex linear. I already know that it is linear over the real number field, because, well, the FR pieces are as such. But now I already convinced myself that I can pull out complex scalar, so it's indeed complex linear. And by, well, this property up here, let's give it a star, this one, and by star, so does it reproduce the small f, so f of y, let's fry plus I, fr minus iy, so here y will be in the subspace, but remember fry, that is the real continuation from Hahn-Banach, so this is just f of y, not f of y, the real part of f of y, real part f of y, and the other one similarly, right? So this is plus I real part f of minus iy, and this is by the yellow star equal to f of y for all y and y. So indeed, it has the desired continuation property. Now what remains is the domination. It now remains to prove the inequality for f, right? So that the complex modulus of f is at most equal to p of x for all vectors x and capital X. All right, so given any x in x, use polar representation, so pick theta in 0 to pi, so that f of x is in polar form complex modulus times the angle. All right, then what do we have then for f of x in complex modulus? Well, it is equal to e to the minus I theta f of x. Now remember, we proved just now that capital F is complex linear. This is this pink underlined stuff up there. So what I can do is I can move this factor inside the argument of f. So f e minus I theta x. Okay. Now the thing is, f, capital F, this is written up here, maybe in green, is the sum of fry, this is the of frx, this is, yeah, I put the star in the wrong place. It is this one that I want. So it is the sum of frx plus I fr minus ix, and fr, this guy is real valued, and so is this, right? This is the decomposition into real and imaginary part. So, but now if I use this down there, using that I start with something real and using the formula with the green star, then it is precisely equal to fr e minus I theta x, right? Because it's a real number here on the left. That's what's underlined in green. So that imaginary part up here necessarily has to be equal to 0. Okay, so that one would fall out, and then you just have this part here in the front, frx. And then here x is e to the minus I theta x. Okay, you have this, and then you pull the same trick. You have a real number, which is, of course, always at most equal to its absolute value. So you have this, and now you use the knowledge that fr in absolute value is at most equal to p minus I theta x, and now you finally exploit the full rotation invariance, the full symmetry of p, because this is equal to p of x, and that's what you wanted, right? So you read the inequality from left to right, f of x in complex modulus at least p of x. Okay, and that's it. That completes the proof of the complex Hahn-Banach theorem. All right, very nice, very nice. Okay, so what we will now do is we will extract various corollaries from the Hahn-Banach theorem. So we will now no longer distinguish between the real and the complex version of the Hahn-Banach theorem. We will extract various corollaries, and well, to tell the truth, these corollaries up front, they might seem strange, it's not so clear why we are interested in them, at least when I first took a class in functional analysis some time ago, 15 years ago. I didn't realize what they are useful for, but rest assured, they are mighty useful, and in time in this module you will learn to appreciate them. Okay, so let's do that. Several corollaries. So the first one is the following. This is the sort of the most typical way in which one uses Hahn-Banach. Remember, we stated it in general vector spaces. There was no norm on it, and P was an arbitrary convex symmetric function. Now we will specialize things to normed linear spaces. Okay, so this corollary, the first one here, it doesn't carry that much weight because, well, we proved that we had a much general result. Okay, but anyways, let's write it out. So let X be I will write this now one time, but afterwards no longer. It can be either real or complex. It doesn't matter because we have both versions of the Hahn-Banach theorem. So be a real or complex NLS, and Y a subspace. All right, then given any, well, bounded linear functional on Y, so F in the dual space of Y, there is linear functional on the full dual space of X that reproduces or extends, rather, I should say, the small f, and the operator norms of capital F and small f, they match. Okay, so this corollary is very close to what we had with the BLT theorem, right? Remember this, you had these densely defined linear transformations, and you can lift them to a linear transformation on the full space X, provided the target space is complete, and the extension was achieved in such a way that the operator norms are equal to one another. This is very much what goes on here, but notice we are working with linear functionals, and we don't require any density or closeness of this subspace Y, right? So this is still, I would say, this is still an algebraic result, although the norm shows up now for the first time. Okay, so let's prove it. Well, there's not much to be done. This is a specialization of the Hahn-Banach theorems. So this is immediate from the Hahn-Banach theorems. Theorems with, well, P of X being just a norm. So the norm is a convex function. This is the triangle inequality, right? It's a convex function, and it is a symmetric function. That comment I made when I introduced the symmetry. So you use it equal to that norm, but not quite. You have to multiply it by the operator norm of the given functional f. Okay. Y for the extension capital F X to F satisfies, well, remember it is bounded above by P, so that's why here in our case it is bounded above by this, and now you see why I need to multiply it by the operator norm of small f, and thus optimizing it, you see that the operator norm cannot exceed, the operator norm of capital F cannot exceed the operator norm of small f. However, Hahn-Banach guarantees that these two linear functionals match, are equal to one another on the subspace. Yeah, but that means then in turn that the two operator norms have to be the same, right? They cannot be, capital F's operator norm cannot be strictly less than the operator norm of small f, because on that subspace they match, and when you compute operator norms you have to optimize over the whole space, right? So you can't have strict inequality there on y. So in fact capital F is equal to small f in operator norm. Okay, and that's it. All right, so that's the first one. Now the consequences will start getting more interesting. Corollary A. In fact, no. Okay, in my lecture notes I enumerate those guys, but here in the videos I never used any enumeration, because otherwise there's too many numbers floating around. So what I wanted to say is that first consequence here up here, this is you can see many lecturers stating the Hahn-Banach theorem in this way from the get-go. Not working with these convex symmetric functions, but right away with the norms. And okay, that's fine. I did it as slightly, more general. Anyways, now the first sort of non-trivial corollary. So let X be a NLS. Again, either real or complex, doesn't matter. And X star its dual space. Now, curiously enough, for any x naught in X, there exists a linear functional so that f of x naught is equal to the norm of x naught. The operator norm of f is equal to 1. In particular, this means for any non-zero x naught, there exists a linear functional that maps that element not to 0. Okay, so why is this curious? Because remember, earlier on, before we, on the first day when we started discussing Hahn-Banach theorem, I said at the moment we don't really have any tools to prove that in general non-linear spaces there's plenty of linear functionals, right? Unless we're in the Hilbert space case, because then we get those inner products. But in general non-linear spaces, it's not so trivial to show that there's actually plenty of linear functionals. Yeah, but this guy here, that corollary precisely says that there's an abundance of linear functionals. In particular, for any non-zero vector, you can always find a linear functional which is not the zero functional, that's what's written there, such that f of x 0 is different from 0, right? So the dual spaces are sufficiently rich that that's one of the first important consequences of Hahn-Banach theorem, and it's this corollary, all right? So proof, well, set y equal to the linear span of that element x naught. So alpha is just a scalar. So the linear span of one element set is just, scalar multiples of that element. And define G from y to f by G alpha x naught as alpha times the norm of x naught. Then I say clearly G is a linear functional on y. So careful here. So the x naught is a fixed vector. So linearity here for G means that you have to look at alpha 1 plus alpha 2 times x naught, not some x naught 1 plus x naught 2, right? Because the subspace is just all multiples of x naught, right? Yeah, but this is here obviously linear, because by definition you have this, and this is, we just multiply the norm into those two scalars. You have G alpha 1 x 0 plus G alpha 2 x 0 in norm. Okay, so linearity is clear, and the boundedness is also clear, because the operator norm of G on that y is at most equal to the norm of x naught, which is finite, right? So this is a bounded linear function. All right, and it's scalar valued, because scalar times norm is a scalar. All right, good. So let's have this. We have that with, moreover, if you now take the absolute value or complex multiples of g of y, then you have alpha x naught, and by the norm properties, this alpha now goes in, and this is the norm of y, right? So you have this for all y in y. Hence, by the last corollary, there exists f in the dual space of all of x with f of y equals to g of y for y in the full space, for y in the subspace, sorry, that subspace that I defined. So f of x naught is then equal to this alpha equals to 1 is g of x naught, alpha equals to 1, which is equal to x naught. That was the first property that I claimed, and the last corollary guarantees that the operator norm of the extension is equal to the operator norm of the initial linear function. But since g of y is equal to y, we have that the operator norm of g is actually equal to 1. All right, so f in operator norm is equal to 1, and that's it. Okay, that's the statement. This in particular, that is of course a consequence of the first statement. If your vector x naught is different from 0, then its norm is different from 0, so f of x 0 is different from 0. Okay, good. All right, so this is the first, I would say, non-trivial corollary, which states that in normed linear spaces, the dual spaces are really big. Okay, there's plenty of non-trivial linear functionals. Okay, in the next video, I will discuss several other consequences of the Hahn-Banach theorems. See you then.